right, people. Jeez, there's 99 people in chat rooms. How does that happen? Actually, it's 111. And yet there's only 61 participants. Oh, whatever. Me and technology, huh? So I want to remind people once again that I'll be coming up with sample questions for the midterm. Midterm's still 4 weeks away. Nothing really to worry about at this, well, nothing to panic about, that's for sure. And it's going to be very, very, very well explained. No surprises. Take home 24 hours and not made excessively difficult or anything like that. I don't want to do anything like that. I would like to see everybody who's put in, a reasonable effort at least to be able to come out with this with a reasonable grade. A good grade, in fact. And also, don't forget that your opinions are valued here. You're going to be part of the quantum computing community as we develop it here in conjunction with local industry and UBC. UBC has a budding quantum information program. And your input as to this course is invaluable. I can't stress that. Your opinions can be given to me personally and also anonymously on Slack as soon as we set that up. So, are there any questions? Can you hear me?
Yes.
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 Great, that's great.
Yes.
So okay, so you notice that the sphere is a continual theme in this this series of lectures. Of course, that has to do with the blogosphere. Let's just talk briefly now about where we're headed with this. What is this week 2 PowerPoint supposed to be about? We're now in the last hour of week 2, and I'm just beginning this PowerPoint at this time. I'm going to greatly simplify it for you. So it's I want to give you an overview of the applied mathematics in full detail so we can see what it looks like, get it over with, and then, of course, I'll give you the simplified version. We're going to talk about the probability theory that's necessary to understand quantum mechanics, at least. And in particular, the first appendix of the last PowerPoint that was on Scott Aronson's view of how to approach quantum mechanics is very valuable in this regard. It makes quantum mechanics much more simple to think of. You know, the idea that it's just about a violation of one of Kolmogorov's axioms right here, and we'll talk about that here briefly. Born's rule, basic linear algebra that you should know, and what do I mean by advanced linear algebra? So we'll talk about those things, okay? Also, don't forget that that is all we really covered last week and the first half of today. These 3 papers, and of course, assignment 1's papers, one of them's the same, that one right there, that PowerPoint. Okay, and now this is what we're going to do, and you'll notice, of course, this is the chapters 1, 2, and a bit of 3 of your textbook. Today, we're talking about that PowerPoint. It's 150 pages, part 3. I'm not asking you to read that at all, but it's explained in great detail, a lot of elementary approaches to all the different mathematical subjects. However, the 20-odd pages of section 2.1, I feel are better. That's where you would have learned it in the first course that you took in order to get in this course in the program that actually does develop. And of course, because you haven't taken that course, you're going to be exposed to the math, but I'm not going to force you to know it inside and out, and you'll see how that's done today. So you've already had this section sent out to you, plus the solutions to the 50-odd problems that are in there. You don't have to memorize those solutions. Remember, it's open book as well. You got nothing to panic about. As long as you get the idea of what it's all about and you know where to go. Here is the website eventually, it's not there yet, that I'm going to give you so that you can join the, there'll be a collaborative website there, a place for you and your peers to place your statements about how this course should proceed. Constructive criticisms. So I want to review what we're trying to do here. We have three main goals. You've all watched this, I hope, the IBM Quantum Experience. It's a 3-minute long video. I think that was something. Did you watch that? Have I told you to watch that? Now I'm getting confused.
You sent it this morning before the lecture.
Good. I sure hope so. And so if you did watch it, you can see that basically they're showing you how to program via, how programming works via a sort of a first generation language approach, using just binary. Whereas this person right here, that next one I showed you, which was the video I showcased at the end of the last PowerPoint, talks about sort of a second generation approach using these quantum computing virtual machines, a Python-based sort of, I don't know, I guess you could call it assembly code. It's sort of a second generation approach. So that's how we're going to learn these things, but eventually that's how we're going to program these things in a much nicer way. So here's first generation, second generation, third generation, and the analogy of what we're doing in this course. And in particular, you also have to eventually be able to read this paper. That is the second goal of this course. And again, that's put out by, you can find it here, in case you haven't looked at it already. And you should watch this video by one of the authors of this paper. And they're from Rigetti. This is a really outstanding paper. This individual knows his stuff. He's on top of it. His video is extremely enlightening, and you should watch it, especially considering you have to understand his paper. Finally, the third goal is, in order to do these things, you have to understand the math. So let's do that. Preamble on the mathematics of quantum computing. So your textbook has a preliminary test in part 3. So for example, it asks, is this function, which is a mapping from the set of reals to the set of reals, where it's assigned as x plus 1, the function t of x is simply x plus 1. Is it a linear transformation? Sorry?
I'm pretty sure it's not.
No, for sure it's not. It doesn't satisfy the definition of a linear function. Very good. Does a binary operation have anything to do with binary code? That's just a completely stupid question. Just ignore it. Obviously, they don't have anything to do with each other. Which space is a bigger dimension, R4 or C2? Well, they're the same, okay? Clearly, this being the definition of linearity for functions, a linear transform, that t of these, the sum of these two variables u and v is simply t of u plus t of v, and also the multiplicative t of cu, c is a scalar constant, equals c times t of u. If it satisfies those two, it's a linear transformation. This one does not. C4 and C2 are the same dimension. Complex numbers have 2 dimensions, so therefore the cross product C cross C is 4-dimensional. Then there's this set of questions. All this bracket notation. So it says, are these things numbers, vectors, or matrices? So first of all, if I tell you that that thing is the inner product of some kind of basis 0 and 1, if I tell you that's an inner product, that it's a generalized dot product, then you'd know that that should come up with a number, right? This is the outer product, on the other hand, so it's not going to give you, like a cross product gives you something that's another vector, really. But this is not a cross product. This is a exterior product. You probably never heard of them in your linear algebra course. But basically, it's a way of going to higher dimensions. And so, that's not going, it's going to give you a matrix, basically. If these two are vectors, that's going to give you a matrix. What's this one going to be? C. That's a scalar. That's a vector, so it's a scalar times a vector. This thing, forget about it for now. So what we have here is a generalized dot product, is the inner product. The outer tensor product is a generalized exterior product, not a cross product. Inner product times a ket vector is C, and something unusual for D. Nothing to worry about now, but we'll see something like it shortly. And here you can see how you can answer the fourth question, really, the way your book does. Give an example of a Hermitian operator whose eigenvalues are not real. That's a dumb question too, because we just said a Hermitian operator produces real eigenvalues, and we'll prove it in this PowerPoint. So let's look at this now. Let's really look at just what the math looks like in quantum mechanics. Let's just look at it. You're not going to be responsible for this, but those of you that are at least in an advanced position, I like to, sort of have track 1 and track 2 lectures. Track 1 being, this is the way the course is, and track 2, this is, for those of you that are a little advanced, but nobody's going to be responsible for it. And so, for example, anybody know what this thing's called?
Schrodinger equation?
That's Schrodinger's equation, exactly. And this is some kind of crazy operator. Usually when you have a caret or a hat on top of a letter, that means it's an operator. H bar is the reduced Planck constant. I is the imaginary unit, square root of -1. That's a time derivative, but a partial time derivative, which says that the wave function psi is a function of many variables, and it is space and time. And here we're taking the time derivative. That is all this thing is right here. And so let's see what that means. All right. Remember, there's no consensus on the intelligibility. We don't have to understand. We don't have an understanding nor the natural language to describe it. But the formal language of math does a great job. In other words, remember, shut up and calculate. It's by a famous quantum mechanist called David Mermin. So I'm not trying to be rude. It's just a catchphrase among the community of quantum mechanists. So this is the double slit experiment that we want to look at and to see where these hacks come from, okay? And what I mean by hack is, for example, the collapse of the wave function. We've never seen it observed. We don't know what's really going on there. When you look at it, the quantumness, this probability distribution, just completely disappears, and the quantum world collapses to the classical world on any kind of measurement or decoherence. So this is the original experiment involving electrons, which at the time you might think, whoa, those are particles, aren't they? So this is back to the beginning. If you've got particles streaming through these slits, it should produce that pattern. But in fact, it produces a wave-like pattern that is reminiscent of a wave-like phenomenon. So if we have a look here, we've got wave interference patterns based on the constructive and destructive interference patterns of these circular wave fronts that are coming from these sources. We cannot predict exactly where a given electron will hit the screen, but I thought an electron's a particle. No. But we can only determine the distribution of locations. That's a probability distribution. And so complex numbers encode this amplitude, as we've already said, because the amplitudes of the individual ones don't add up classically. It doesn't add the way you would think. And what that means is matter behaves in a random way, and matter exhibits wave-like properties, and we call those probability waves. We've already seen that. And so Born's rule says it's going to look like this, okay? The wave function is going to look like this. It's the probability of distribution for a particle's position, okay? And so it's normalized so that it is a probability, and you can see this is, the full nature of how it's done in quantum mechanics. And so this wave function clearly has to satisfy some sort of wave equation. But this is the big deal right here, once again. That the fact that Kolmogorov's third rule right here, the basic axioms of probability theory, isn't satisfied. And so what do we have here? Probability of an event is real number greater than 0 or equal to 0. The probability that at least one of all possible outcomes of a process, such as rolling a die like this thing, will occur is 1. Now, finally this one. If two events A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A occurring plus the probability of B occurring. That means that makes no sense. Don't you see? This is what we expect, but it doesn't happen. It's not equal to that, as we saw in the last PowerPoint. Is everybody absolutely clear on this point?
Yeah, you can have negative probabilities.
Exactly. And so this is really what's happening. That is being violated. This is where probability starts coming in. Now, listen very carefully. The double slit experiment seems to violate axiom 3, but this is not true if the notion of these axioms can be generalized to so-called non-Boolean algebras. You don't have to know about this. That means Boolean analysis that views the meaning of and to be intersective, and the non-Boolean analysis is attributed to a weaker meaning. You can go here if you want to find out more. Basically, all we're saying is we're going to allow for these amplitudes, okay, these complex amplitudes. Therefore, non-Boolean. It's a fancy way of saying what we've already done. Everybody with me? So, here, slide number 37 is something I want you to pay close attention to. It is very busy. Are there two kinds of probability theories? Yes. Quantum probability developed in the 1980s as a non-commutative analog of the Kolmogorov theory of stochastic processes. You don't have to know exactly what that means. I don't expect many of you have actually had a lot of probability theory. If you have, you'll be lucky to have just seen it in Macam 101. So like Scott Aronson says, quantum mechanics is easy once you take the physics out of it. It's just this. That's a stochastic matrix operating on a probability vector, producing a new probability vector, where in this case, you're dealing with this normalization condition. It's called a L1 norm, and that's a stochastic matrix, whereas in quantum mechanics, it's slightly different because of Born's rule, we have an L2 norm. What's a norm? That's the metric that you use in your vector space. I'm going to define that shortly. And so it's here we use a unitary matrix instead of, in classical probability theory, a stochastic matrix. Whew! Well, you can read Scott Aronson's paper once again for this. So what have we got here? We got probability theory, probability spaces, just like a Hilbert space, complex amplitudes, L1 and L2 norms, unitary versus stochastic matrix, and a thing called the expectation value, something we'll really need to talk about next week. So in one slide, let's go back. It is important to understand why Scott Aronson calls this quantum mechanics in one slide. I want you to really focus attention on slides 37 and 38, please. Take special note of those, because if you get that, you're way ahead of the curve. You have to eventually understand the relationship between these two pictures right here. Standard probability theory, I'm not asking you to review it, but just enough so that you understand what these things mean here. Now, what do we mean by L1 and L2 norm? Let's get to that. First of all, I'm going to just say the expectation value is the average value of an observation when measurements of that observable are made on a large number of identically prepared quantum systems. Look, it's probabilistic, people. You have to keep repeating your measurements. And so there has to be this averaged weighted value. Why is it weighted? It's weighted by the probability distribution that's defined by the wave function. So if it is used frequently in quantum mechanics, well, it is, because since measurement outcomes are probabilistic rather than deterministic. For each observable Q, there is a Hermitian operator bold Q. I tried to put a hat on it, couldn't do it. When the quantum system is in that state, there's that weird bracket notation, and an observable Q is measured in an experiment, one obtains the eigenvalue of the operator of Q. Therefore, the expectation value, which is found by this strange conglomeration of brackets in a given quantum state, that's a quantum state right there, can be found by summing the probability of measuring a particle eigenvalue of this operator bold Q multiplied by that eigenvalue over all possible measurement outcomes. That is the expectation value. It's a weighted average. That's all it is. And believe it or not, it's a difficult concept for physics students. So this slide number 39, please know it well. Okay, at least look at that for next week. Any questions about this? This is just a brief introduction. What's this thing right here, you might add? Well, let's have a look at that. I sent you out a beautiful, fantastic, let's see, how's Trump talk? I sent out a really beautiful, it was a beautiful paper written by some really fine people. Not working? All right, so never mind. I sent out a set of notes from a website which is based on a Wikipedia website regarding bracket notation. So here, from your bracket notation reference, which has been sent out, you can see where this comes from by reading this. So this notation is going to become very important next week. Start getting used to it. Make sure you read this paper that was emailed to you today along with this PowerPoint. Questions? Then the first postulate of quantum mechanics basically says that an L2 norm produces a square integrable function. Why? Well, because it's got to be square integrable because it's imposed by this Born rule. It's got to be integral, meaning that that has a finite probability. Okay, and so what do I have here? Square integral. This is to satisfy the fact that we're dealing with a finite probability density. The L2 norm naturally leads to an inner product space. And it has to do with the fact that the Born rules force this on us. This right here, this idea that it's complete, simply means that I can apply the limit and therefore these integrals can be taken. Hilbert spaces provide the necessary geometric structures to formally represent linear transformations, the evolution of state space. Okay? So the second postulate is, in fact, Schrodinger's equation. That's what it looks like. We have things like causality being maintained in the evolution of the wave function. The superposition principle has to be maintained, and it corresponds with everyday physics. That's what the correspondence principle means. In case you're wondering where this Schrödinger equation comes from, it didn't come from, remember I showed you that book? I learned it from this book, from this guy at UBC. Well, that book shows you an alternative formulation of mechanics that isn't based on Newton's laws, but this thing called the principle of least action. Also, the Schrödinger equation is linear by construction, and you can see through the superposition. This thing you can look at. I mean, you haven't seen partial derivatives, but I don't think that's too hard to figure out, though I'm not going to make you responsible for a single partial differential equation. But that's just for those of you that can look at it. And finally, the square integral nature of state functions, or state space for quantum mechanics, arises from Born's rule. And we call that an L2 space. Your book talks about it. What the heck does that mean? Well, first of all, you're supposed to be saying that this is kind of crazy for a class with your background. You know, like, hey, man, I thought you just said we need matrix algebra. And it's true. I thought I'd just show you what it really looks like in its full glory. So the previous slides are intended to demonstrate that quantum mechanics is probabilistic and described within the framework of a complex vector space so that we can produce a very simple linear transformation structure. In the circuit model of quantum computing, that's sort of the first generation model view of looking at it, which in fact is equivalent to a quantum Turing machine. Qubit states implicitly evolve according to the Schrödinger equation by applying quantum gates, taking the form of a linear transformation. So just like we use these logic gates, that's what we're trying to emulate here. And that's why we don't have to deal with partial differential equations like solving the Schrödinger equation, okay? So we're going to spend the rest of the time developing a keen understanding of this. So let's do the linear algebra really quickly now. By the way, that's actually a Hilbert space you're looking at there, with a bit of art attached to it. Any questions before we tackle this part of the course?
It's me again. I have one question.
Yes, please.
On page 43, I think. 42. I was wrong.
Okay.
Okay, yeah. So for the top equation, it says the integral of what I think the absolute value of the wave function squared is less. Isn't that, or is that defined to be equal to 1 due to?
Yes, it is. But this is just a statement of what's known in advanced linear algebra as a square integral. That means that it's defined. That's all it means. But yes, in fact, it is 1.
Oh, okay.
So this is a condition that just basically says that you're going to have a finite probability, and it is in fact 1. And you're correct in what you said.
Okay, thank you.
All right, thank you. Good point.
I have another question.
Of course.
So this is to do with traditional probabilities versus
Yes.
quantum probabilities. And so my understanding here is that quantum probabilities are complex numbers.
No. Quantum probabilities are just as you say, they're from 0 to 1, but they're based on complex amplitudes. You have to take the square of a complex amplitude to get your normal notion of probability. So that's how they can become, constructive and destructive in an interference pattern. But it's because that's the one step we've gone further beyond a normal probability theory, and that's really it. It's just simply that there's a precursor state of complex amplitudes. So I'm sorry to interrupt.
No, that helps. And then also, would the destructive or constructive interference happen before or after the squaring to produce the probability?
Well, when you take the square, that's like, okay, that is just telling you where, okay, let's have a look here. This just simply tells you that the square integrable function means you're dealing with an L2 norm, which means, well, it's forced upon us by the having to take the square of a complex amplitude. All of this takes place before measurement. This is the first postulate. This just tells you what the thing looks like in state space, which you never get to look at. You cannot look to what's going on in the quantum world. When you do, it collapses. And when that thing, actually its evolution is done by these unitary transformations, right? So there's this unitary evolution, which you actually can't see. You can manipulate it, but you can't see it directly. Your only way of actually peering into the quantum evolution of the Schrodinger equation is through these unitary transformations, but you can't see them. It's indirect. When you actually make the measurement, then you're applying a Hermitian matrix or Hermitian operator, which forces collapse of the wave function. After all these crazy things have happened with your quantum circuit, talking in terms of quantum computing, after you've done all that manipulation to get that pattern of probabilities the way you want it, which maximizes the right answer, then you force a collapse of the wave function. But otherwise, you don't know what's going on in there at all.
Okay.
All right. Anybody else? These are great questions, man. Keep them coming. All right. So I think it's important for you to appreciate that there's another formulation of mechanics that doesn't involve Newton's laws, but you don't have to know that for the course. So all of this stuff here that we talked about is FYI, okay, for your information. That's why I put that there. You're supposed to, you're supposed to realize that, that was an introduction. So this was that explanation. Let's talk about the linear algebra now. The first thing I need to at least describe is what I mean by advanced linear algebra. And so you all had introductory linear algebra, which, has all the common stuff that we'll talk about shortly. But truly advanced linear algebra has something like a complete complex inner product space. In other words, a Hilbert space. Function spaces, that's a Hilbert space. Unitary and Hermitian transformations. Outer products, you've never talked about outer products in your standard course in linear algebra. So those are the things that we've already alluded to. Okay, so let's review the basics. And here in one nutshell, let me show you, you see this person right here? Gilbert Strang. Do you see that, people down there, the author of that? That at least I mean, it's quite remarkable. You know how there's certain people who are the hallmark, the leaders of a field, the people that are looked up to. Well, when I was an undergraduate, and that was a long time ago, to this very day, MIT professor and mathematician Gilbert Strang, his textbook on linear algebra is still considered the best. And he's still alive and he's still publishing. And this is a recent slide that he's put out for the way he sees linear algebra, the introduction to linear algebra from OpenCourseWare at MIT being organized. The idea of independence of column vectors, LU decomposition, you've seen this before, the orthogonality of column vectors, eigenvectors and eigenvalues, and all this business about LU decomposition and so forth. We don't have to worry about a lot of that, but that is really a good summary, okay? If you're really interested, I've got a great, well, I have a colleague at one of the double ITs in India who has these two excellent PDF files that I can send you, and I will send you if you want it. They're very good. Please read these. You don't have to do the exercises, of course. All right. So I'll send those out. Okay. So I'll send those out as soon as this is over today. You can see also this is from his textbook, Gilbert Strang's textbook. That is what's considered to be the introductory topics of linear algebra. These are the ones that are important for us: vector spaces, orthogonality, eigenvalues and eigenvectors, and linear transformations, especially linear transformations. So those are things you should review. And well, what is a vector space, right? Within all vector spaces, two operations are possible. You can add any two vectors and we can multiply them by scalars, okay? In other words, linear combinations, that's what that means. And there's a thing called a subspace, no need to go into that. Linear independence, that's pretty obvious what linear independence means. If any other combination of vectors gives zero, then they are dependent. So here's a good example out of the textbook right here. Show that these vectors are linearly dependent. And it's true because you can add them together and get the zero vector. That should be straightforward. This is just review. Spanning a subspace, no need to go into this. Basis of a vector space, you all know what I'm talking about. Dimensions of a vector space. The fundamental theorem of linear algebra. The idea of defining row vectors, column vectors, and the transpose. All of you should know this stuff coming into this course. And you do, don't you? You do, don't you? Thank you for your, okay, linear transformations, stretching, rotation, reflection, projection onto an axis, projection, the dot product, right? So this is extremely important. Also, a linear transformation, it is not possible for any of these three things to happen, okay? It is impossible to move the origin since A times 0 equals 0 for every matrix. If the vector x goes to another position, then 2x must go to 2x prime. And in general, cx must go to cx prime since it's linear. If the vectors x and y go to those two, then again, a linear statement right there. And so we define, watch this, the transformations that obey these rules are called linear transformations. And so there's the definition of linear transformation. You must know that. Transformations that can be represented by matrices, of course, and that they are linear. If x equals this set of coefficients, then ax equals cax1 plus all the way through. You can represent it in matrix form. So what does it say here? The transformation t of x equals a times x, it's like an eigenvalue problem almost, has no freedom left after it is decided what to do with the basis vectors. The rest is determined by linearity. This is incredibly important. That's why we use the power of a linear vector space. The requirement 1, that we just looked at for two vectors, x and y leads to the condition 4, okay? The transformation does have a free hand with the vectors in the basis because they're independent. When those are settled, the transformation of every vector is settled. That's the power of these linear vector spaces, is that everything's taken care of automatically. You have to appreciate that. This is why vector spaces are so powerful as a formal framework for describing physical systems, not just in quantum mechanics. So here's another exercise you can use, thinking now that that ket is a vector, okay? So suppose V is a vector space with basis vectors 0 and 1, and they're thought to be orthogonal, and A is a linear operator from V mapping to itself such that A onto this one transforms it to the other state and vice versa. Give a matrix representation. Well, that's what it looks like, obviously. It's just the inverse transformation. I think you all could see that coming. You can study that a little further if you're not sure, but if it was all zeros except the diagonal being 1, then it would just simply be the identity operator. But the transpose of that is the inverse operator. Here's another exercise. Suppose A is a linear operator from a vector space V to another vector space W, and V is a linear operator from vector space W to vector space X. And here we have these three kets, and they're all bases for these respective vector spaces. Show that the matrix representation for linear transformation B times A is the matrix product of the matrix representations for B and A with respect to the appropriate bases. So we have this representation clearly, and thus you can just run through the algebra. There's the solution. There's nothing new about this whatsoever. It's just regrouping terms. So again, we're just making substitutions, you know, here all the way through, and there's no mystery here. Everybody get that? And you can do this one on your own. The identity, that's really simple, all right? Oh, by the way, what's this symbol right here? Anybody ever seen that before?
Is that the Dirac delta?
Yes, yes. Well, the Kronecker delta. The Dirac delta function is actually like the Dirac delta comb. This thing just simply says it's always 0 unless I and j are equal to each other, in which case it's 1. But Kronecker delta, Dirac delta function is slightly different. Good. Okay, all right. So here we go, fundamental concepts. The power of vector spaces in physics. The physical condition or change in condition of many simple systems has been found to possess a magnitude and direction. And it's natural, therefore, to develop the concept of condition or change in condition using vectors. By expressing various types of problems in a common framework, basically the vector space evolves. That's what we've just done, right? And so the power of vector spaces in physics is that differential equations are commonly at the heart of modeling physical systems. Almost all, like climate modeling, economic forecasting, you name it, it's all based on differential equations. Why? Because they're about related rates of change. The solutions of various differential equations actually gives rise to huge sets of linear equations. What is the point of linear algebra? It's really, what is the central concept underlying linear algebra? Vector spaces. And so you can just keep reading this. We're just reiterating over why we use the complex vector space. Definite values for physical properties such as energy or momentum correspond to eigenvalues of certain linear differential operators, and their associated wave functions are called eigenstates. That's very important for you to know. You all know what an eigenvalue and an eigenvector is. So an eigenvector, in this case, is an eigenstate, since this vector in a Hilbert space is represented as a vector. And then there's this thing, you'll hear about it eventually, it's called the spectral theorem. It decomposes a linear compact operator acting in functions in terms of these eigenfunctions. Put that in your back pocket. Just remember that we heard of this thing called the spectral theorem. If you've taken a course in quantum computing, you're kind of expected to know these words. Don't worry, I'm not going to force you to memorize or work with the spectral theorem in any way. So, that's the basic stuff. That's your review of linear algebra. The more advanced topics, right away they start with complex vectors and matrices, all right? So, it's complex vector spaces, really. And so let's get back to something simple like, well, start with complex numbers. You all know why they're there, where they came from. Anybody know what this equation's called? Euler's equation. Euler's equation for a very special value of theta equals pi. Never mind that. This is an incredible equation for many reasons. Complex numbers are broadly used in physics, normally as a tool that makes calculations easier, due primarily to Euler's equation, and that's right there for x equals pi. That gives you that thing, okay? Quantum mechanics is different from the majority of other fields because I appears right there explicitly in the equation, the complex unit. All right, and so here, look, there's these two great advances in mathematics. One was how to overcome, we're trying to solve polynomial equations, finding the roots of polynomial equations. We couldn't complete them all because there's only so many real roots, and then how do you solve the ones who these quadratics, for example, that are above the x, they're positive leading coefficients, and they don't cross the x-axis. How do you find those imaginary rules? Well, you define this thing without violating division, or taking the even root of a negative number. And so that's where it came from when we come up with the idea of a complex number, which is a two-dimensional number based on real numbers a and b, but we multiply the second one by the imaginary unit. And so you can see here that complex numbers, well, this is the taxonomy. You've got natural numbers, counting numbers, integers, rational, and various types of irrational and real numbers. And then there's imaginary. Pure imaginary is a disjoint set within the set of all complex numbers. It shouldn't be anything new. So the wave function is designed such that it describes the probabilities from the results of measurement, which are subject to the characteristics of constructive and destructive interference. This must embody the characteristics of both amplitude and phase. Amplitude and phase. Amplitude and phase. Phase is contained in that unit there when you think about what a complex number looks like. Quantum mechanics, both amplitude and phase depend on each other, and this makes the Schrödinger equation linear, allowing for superposition. You don't have to know that. A probability cannot be conveniently expressed using just real numbers. It's got to be complex. And in order to do that, we have to have the concept of the complex conjugate. It's not just squaring a complex number. It's because it's a two-dimensional number. In order to make it work properly, you have to have the concept of the complex conjugate, okay? And so, for example, here is a complex number, z equals x plus y, and r is the magnitude, and phi is the phase, measured positive up from counterclockwise from the real axis. And the complex conjugate is its reflection. That is all it is. And that is what's necessary, given these properties, to actually come up with Born's rule. Everybody get that? So that, let's have a look at Born's rule in particular. If you do this, people, why don't you do it now? Everybody, put your fingers really close together and look at a light source and tell me, can you see those black bands parallel to your fingers? Everybody try that right now. You're surprisingly quiet. I want to hear it. Yes?
Yeah.
That's interference. You're actually producing interference of light. Your fingers are close enough to actually be able to produce interference patterns. And so this is for your information. You don't need to know this, but this is how you come up classically using classical waves and using the Born rule. How do you derive the Born rule from this knowledge that we've just gained right here of using a complex amplitude and its complex conjugate? That's how it works. Okay, let's just pass that by. That's all in passing. So this part right here on Born's rule in detail is for your information. Okay, that's the I up there. It is important, but I'm not going to make you reproduce it. Okay, so these slides right here, 87, 88, 89, 90, 91, you are okay to just omit that. Okay? Getting close now, getting close. So as far as vector spaces go, okay, we've already talked about how powerful they are and why we use them. And so we use them to solve sets of linear equations, and you can see we can transform this into a matrix times a vector to give a solution vector, okay? Instead of considering an n by n matrix A as transforming an n-dimensional vector X into a new vector A times X, linear transformations satisfy, of course, linearity. So matrices are linear transformations. That's what we're doing here. We all knew that already. So recall what a vector space is. It has these two properties of addition and scalar multiplication, and it satisfies those properties A1, A2, A3, A4, all the way through A8. That is what it takes to be a vector space. Now, here's some examples of a vector space. The infinite dimensional space R infinity. I don't have to have just 3 dimensions. I can have an infinite number of dimensions. The space of 3 by 2 matrices. Interesting. And the space of functions, because functions actually can satisfy the properties of any vector space, those properties there. If they satisfy these, then you can use them. So a space of functions, and that's where the power of a Hilbert space comes in. So clearly vector spaces can be very abstract. Not only can one form abstract vector spaces in one or in more of the familiar dimensions of physics, but you can have infinite dimensions. One can form different metrics. And so this is pretty big because these functions satisfy these properties right here. You can set up functions as an orthonormal basis set, which span a given vector space, unbelievably powerful. So yes, that's what we're going to do here. You know, we've got this wave function. Contains all the possible information about a quantum particle, and its time evolution is determined as such. And we interpret the probability amplitude by a particle having state R with the probability density given by this thing, this integral right here, okay? Sorry, this integral, which is square integrable. Being square integrable means we use the L2 norm, as we've talked about before. If we have discrete functions, we can set it up in a vector form like this. What do we do about continuous functions, okay? Here, this is discrete. We've got nothing to worry about here. Well, if it's continuous, all we do is just simply make it a complete vector space. Each wave function is associated with an element of a linear vector space F and is denoted by this ket notation, so that these are logically equivalent. And in other words, quantum wave functions form a linear space in the sense that multiplying a function by a complex number or adding 2 wave functions together produces another wave function. And that's what we mean here. So let's talk now, since I just said that you can produce a space of functions, how do you measure the distance between 2 functions? Because after all, a vector space allows you to measure distances. We've got just 1 minute left, and hence I'm going to leave you with that. I'm going to leave you with that idea.
Integrate the square of the distance.
Well, that's exactly what you do. You do this right there. You know, we just do what we're used to doing. Why don't you read this for Tuesday? And for now, please finish reading this wonderful PowerPoint. And I'm going to send you out. I'm going to send you out these papers, which use a ton of exercises. I'm not going to ask you to do them. Those are just for your information. I'm not giving you any more mathematics than you've already seen as far as this textbook section 2.1 and its solutions are concerned. I'm not giving you any more math. And on Tuesday, I'll tell you what to weed out from this set of problems. And when it comes to the exams, like I said, it's open book, so don't panic. Just understand what's what, and that's about it. Everybody good with that?
Do you want us to read the rest of this PowerPoint before?
Why not? That's why I sent it out. That's why you people want it, I think, right? You don't have to, but if you do, that's your choice. How about that? Okay, people? And like I said, after these 2 hours, I tend to be a little frazzled, so I'm not really, if you want to set up a time we can talk, or Zoom or whatever, just send me an email, and I'm always available for you, except perhaps when I'm out riding my motorcycle. Okay, people?
Okay.
All right, then. Ciao for now. It's been a pleasure. Thanks for sticking it out. Stick
Ciao.
with it, people. Stick with it. Stick with it. You're going to get through, I promise you. Take care. Bye-bye.